Hi, my name is Dennis Skiba, and I would like you to join me on this journey to determine the resonance energy of benzene. But what exactly is resonance energy? Resonance energy is the extra stability of a conjugated system as a result of the delocalization of its pi electrons across, in this case, benzene's 6 carbon bonds in the aromatic ring. These pi electrons are delocalized from the p orbitals that are located above and below the plane of the molecule. And when they are delocalized, they confer extra stability to the benzene molecule in the form of resonance energy. So how can we find this resonance energy? A way to do that is using the isodesmic reaction of benzene and cyclohexane to yield CDDT. An isodesmic is just a fancy way of saying that the number of carbon-carbon bonds and number of carbon-hydrogen bonds for the reactants are equal to those of the products. But in the gas phase, we could say that the heat of combustion of benzene and cyclohexane is equal to that of the heat of combustion of CDDT. But this is not true, because in the gas phase, the resonance energy is not accounted for. Therefore, we have to use them in the liquid phase. And I know just the thing. That good old bomb calorimeter. We can use bomb calorimetry to find the heat of combustion of cyclohexane and CDDT in the liquid phase, and then this in turn can give us steps towards finding the resonance energy of benzene. We will not be finding the heat of combustion in the liquid phase of benzene for obvious reasons. Okay, using our best friend, the Hess's law cycle, we can find the enthalpy of vaporization of benzene, cyclohexane, and CDDT, as well as the enthalpy of combustion of these 3 molecules, taking the sum, and then this will give us the resonance energy of benzene. The values associated with A, B, and C will be found by a quick Google search using NIST. Okay, we're that much closer to finding our beloved resonance energy. But first, some hypotheses. So I believe that the heat of combustion of CDDT will be much greater or give a more negative value than that of cyclohexane because CDDT has double the number of carbons than cyclohexane. So I believe that the factor of sheer size alone will cause more heat to be released upon the burning of 1 mole of CDDT as opposed to cyclohexane. Also, we will be comparing our resonance energy of benzene value to the software, computational software Sigris. And so I believe that Sigris will give us a lower, more accurate resonance energy value of benzene because it guarantees the lowest energy conformation of CDDT and cyclohexane, while our experiment doesn't. We're not aware of the conformations of these reagents. Okay, so the experimental method. Within our bomb calorimeter, we purged it with oxygen gas and placed our cyclohexane capsule and CDDT in the vessel, place it into the oval bucket, fill it with water, put the calorimeter lid on the calorimeter jacket, and then put our temperature probe through, making sure it's immersed into the water, and this will give us very valuable temperature readings that can be used to find the change in temperature of each of our runs. Okay, after pressing a button a few times, we are off. Okay, so now, after obtaining our 4 graphs, 2 for CDDT and 2 for cyclohexane, we find the temperature and time of 5 points. And using the equation on the next slide, we find the slope of the horizontal areas of the graph, and this accounts for the change in temperature of the beginning and end of our runs as a correction value. And so using the temperatures from the graphs, we can find the change in temperatures shown on the table. Okay, we're that much closer to finding our resonance energy. But now we need our enthalpies, and the enthalpy can be found by obtaining the change in internal energy plus the product of the change of pressure and volume. But first, to find the internal energy of combustion, we can multiply the heat capacity of the bomb times the change in temperature. Then also the total heat equals the heat capacity of the bomb times the change in temperature. And then finding the heat of our sample, we can take this total heat and subtract the heat given off by the wire as well as the heat of the capsule for the cyclohexane runs. Once we have this total heat of our sample, we can divide it by the moles of our sample to give us the internal energy of combustion. Okay, we're almost there. Using our internal energies of combustion, we can add it to the product of the change in moles of gas times the gas constant and temperature to give us the enthalpy, change in enthalpy. So the change in moles of gas is equal to the moles of gas of the products minus the moles of gas of reactants, -4.5 for CDDT and -3 for cyclohexane. And then doing this calculation, we can find the enthalpy of combustion for CDDT and enthalpy of combustion for cyclohexane for our runs, as well as a computed average. And we can see that one of our hypotheses was right, and the enthalpy of combustion is just about double that of the enthalpy of combustion of cyclohexane. Okay, one final step, determining the enthalpy of vaporization of CDDT. So using the data from the lab manual, we can take the natural log of the pressure and plot it against the inverse of time to get our slope. And then using the Clausius-Clapeyron equation, we can associate the slope-intercept form, taking the slope, multiplying it by the gas constant to give us an enthalpy of vaporization of -47.675 kilojoules per mole. Okay, we have everything we need. Now, we can take the summation of all of the values shown on the screen to give us the resonance energy of benzene. The enthalpy of vaporization of benzene and cyclohexane, as well as the enthalpy of combustion of benzene, were literature values determined by giving it a quick goog. And then we have our beloved resonance energy of benzene, which is 222.104 kilojoules per mole. Okay, so how does this compare to our computational model, Cygress? Using Cygress, we found the resonance energy of benzene by subtracting the heat of formation of products minus the heat of formation of reactants to give us 153.56 kilojoules per mole. Finding the percent difference, we found a difference of 44.64%. So we can see that our other hypothesis was correct in that Cygress gave us a lower resonance energy of benzene. Okay, so back to the drawing board. With this experiment, there are many things that we don't account for and that could go wrong. So let's start off with one of them. A more accurate determination for the temperature and a better way to probe the temperature. So the max temperature is a key value in finding the change in temperature of each of our runs. And the max temperature had a lot of fluctuation, so it was hard to give a very accurate determination. If we had a better temperature probe, this would solve this issue and give us a more accurate delta T, which would lead to more accurate subsequent calculations. Also, due to our great efficiency in the lab, we were only able to obtain 2 runs for CDDT and cyclohexane. If we were able to get maybe 5 runs, this would give us more validity with our data, but 2 runs doesn't give us much accuracy. Also, there's no way to ensure that the heat being given off by the CDDT or cyclohexane is being fully contained in the bomb vessel. It could be being released in the bomb jacket or in the calorimeter, and there's no way of tracking that. Okay, so determining alternate methods of resonance energy of benzene. First, we could consider the heat of combustion of cyclooctatetratriene, which is the molecule shown on the right. So a cyclooctatetraene has 1 more double bond in comparison to benzene. We can find the heat of combustion of this double bond and subtract it from that of cyclooctatetraene to give us a reasonable estimate of the resonance energy of benzene. And so getting this bond enthalpy calculation, can we use bond enthalpy on its own to determine the resonance energy of benzene? We cannot. Bond enthalpy does not account for the resonance energy of a molecule and just only refers to a single conformation. Another method we could explore is the heat of hydrogenation of cyclohexene, the molecule shown on the left. So if we hydrogenate across this double bond and multiply the value by 3, we can take this heat of hydrogenation and subtract it by the heat of hydrogenation of benzene to give us an estimate for the resonance energy of benzene. Also, as discussed previously, Cygress versus other methods. Our Cygress approximation gave us a lower resonance energy as compared to experimental, and ultimately, it could definitely be more accurate as as discussed by the conformational analysis previously. Okay, so why does benzene have so much resonance? One factor of this resonance energy is that the delocalization of the electrons in cyclic molecules are better as opposed to their linear counterparts. But then why is the resonance energy of benzene greater than that of cyclooctatetratriene? This is because the 6 pi electrons of benzene abide by the Huckel electron rule for n+2, while the cyclooctatetratriene does not because it has 8 pi electrons, making it non-aromatic. So these are some of the factors that contribute to the high resonance energy of benzene.